All right, this will be very similar to part 2, where we had molecular geometry practice, and I will first go over the rules of the experiment. Solve the molecular geometry of each particle. Formula of particle, approximate shape, total valence, total bonded electrons, total outer atom electrons needed to complete the valence. Show how the balance of the electrons are calculated. Conclude the totals, sockets, bonded electrons, and non-bonded electron pairs. Draw the final shape and include any non-bonded electron pairs. Calculate and insert the dipole moments. Determine the polarity. Draw a conclusion regarding bond angles if they are distorted due to asymmetry. Make a model using clay and toothpicks for each particle in the practice problems. I will check your progress during the experiment. Here are the 10 particles we will do, and that is going to be N3, -1 charge, the polyatomic ion, sulfur tetrachloride, water, phosphorus pentachloride, sulfur tetrafluoride, iodine, tetrafluoride, -1 charge, and then we'll have sulfur dioxide, carbon dioxide, that is chlorite and chlorate, each with a -1 charge. So let's start with N3, -1 charge. And so that is going to be the particle. Notice it has a -1 charge, so you'll add an additional electron. So there we have the arrangement. We don't know if it's going to be linear, but that's all the information we have. So we have 5, 5, 5, and -1. So that's going to be 16. And then we will subtract 4 for the bonding. 2 times 2 is 4. And then that will give us, well, let's do the total electrons for the outer atoms. And that's going to be 2 times 6 is 12. Now we're going to do the accounting. So we get 16 minus 16 is 0. So it's going to be linear. But the central atom is going to be a nitrogen. So it's going to be 2 sockets, 2 bonded, 0 non-bonded. The parent geometry is a linear. And the nitrogen is the central atom. So you're going to have to put in 2 double bonds. And it'll be linear because each double bond looks like a single bond. So that's going to be what the shape actually looks like. So you'll have the central nitrogen has 8 bonded electrons and no non-bonded electrons. The particle is clearly linear. Clearly linear. A little confusing, but not too bad. No dipole, no polarity. Everything is fine. It's a non-polar linear molecule. The reason there's no dipole, there's no shift. There's no shift. So bond symmetry, yes, absolutely, and no polarity. Okay, sulfur tetrachloride, SCl4, that's going to be number 2. And the geometry, we're going to guess, is probably something maybe tetrahedral, but we don't have enough information. So we know we're going to have 34 electrons. Add them up. 6 plus 28 is 34. We're going to have 4 bonds. That's 8. And then We have 4 outer atoms, and so we have 4 times 6 is 24, and that will give us 32. 34 minus 32 is 2, so we have 1 pair left over. So we have 5 sockets, 4 bonded, 1 non-bonded, and so we're going to put that excess electron pair around the central atom, so that will be a trigonal pair. So now let's read, I have a note on the next slide. It says, there are 5 sockets on the central atom. The sockets contain 4 bonded pairs of electrons and 1 non-bonded pair. The parent geometry is trigonal bipyramidal. There are 3 trigonal pair atoms 120 degrees apart and 2 polar atoms 180 degrees apart. In sulfur tetrachloride, the lone non-bonded pair is in the trigonal planar site. So it's going to be around the trigonal planar plane. And the geometry is going to be seesaw. Chlorine, that's chlorine. If you take it out 2 centimeter figures, 2 decimal places, 3 centimeter figures, and sulfur, so you have a little bit of a dipole shifting towards the chlorine, and you have no bond symmetry, and it is going to be polar. So the polarity is yes. Now, a very, very familiar molecule, H2O, otherwise known colloquially as water. So it's HOH, and without any information other than just those 3 atoms, we'll put down linear. Okay, so we know it's going to be 161, and it's going to be 8. That's going to be the total valence. And then we're going to subtract 4 off because of 2 bonds. 2 times 2 is 4. And the hydrogen does not need any additional electrons other than the 2 in each bond. And therefore, I have 2 non-bonded pairs to be placed around the central atom. 2 non-bonded pairs to be placed around the central atom. And so I have 2 bonded pairs, 2 non-bonded pairs. And so, therefore, it's going to be like that. There's the 2 non-bonded pairs. And it looks very similar to tetrahedral. And it's going to be, here's a note, there are 4 sockets on the central atom. The sockets contain 2 bonded pairs of electrons, 2 non-bonded pairs. The parent geometry is tetrahedral. The parent geometry dictates the internal geometry of the HOH bond angle to be 109.5, but the influence of the 2 non-bonded pairs puts it at 104.5 around. And therefore it's going to be bent or angular geometry. If you put the dipoles in, you can clearly see by now that the molecule will indeed be polar. So the oxygen is more electronegative than the hydrogen, and you have no bond symmetry, and you have polarity is yes. Okay, phosphorus pentachloride. Phosphorus pentachloride. So we put it around as if it's quite possibly trigonal bipyramidal, and we have 5, and then 7, 7, 7, 7, 7, it's just 40. And then we're going to subtract off 5 times 2 for 10 electrons in the bonds. And then we'll have 5 times 6 is 30 for the outer atoms to complete the valence for those. and therefore we will have 0 left over. 40 minus 10 minus 30 is 0. So 0 non-bonded pairs to be placed around the central atom. So you have 5 sockets, 5 bonded, 5 non-bonded. Therefore, it's going to be a shape like that, and it will actually be trigonal bipyramidal. There are 5 sockets on the central atom. The sockets contain 5 bonded pairs of electrons. There are 3 trigonal planar A atoms, 120 degrees apart, and 2 polar B atoms, 180 degrees apart. Therefore, it's going to be trigonal bipyramidal. And if we put in the dipoles, we'll have them shifting towards the bond, the cloud, shifting towards chlorine, and they are all, we have bond symmetry, absolutely, and we have no polarity. It is a non-polar molecule. Now we're going to do sulfur tetrafluoride, and we have sulfur and 4 fluorine atoms, and we're going to calculate the total valence to be 34. And then we have 4 bonds times 2 is 8 electrons, and then we have 4 fluorine atoms, and times 6 is 24, and that gives us 2 electrons left over, so 1 non-bonded pair to be placed around the central atom. So we have 5 sockets, 4 bonded, 1 non-bonded. Okay, so we have the non-bonded pair, and we can clearly see a little deja vu. There are 5 sockets on the central atom. The sockets contain 4 bonded pairs of electrons A and 1 non-bonded pairs B. The parent geometry is trigonal bipyramidal. There are 3 trigonal planar atoms 120 degrees apart. That's A. And 2 polar atoms 180 degrees apart. That's B. In sulfur tetrafluoride, the lone non-bonded pair is in a trigonal planar site, and that's A. And so we have the seesaw. Should be similar. We did the sulfur tetrachloride as well. So I'll let this run, and you are going to have the dipoles put in, and it will come out to be, it'll be no bond symmetry, and polarity will be yes, absolutely. Okay, next we have iodine tetrafluoride with a -1 charge, and that's what we're going to approximately put. We'll calculate our valences, and it's going to be right away 35. That should be fairly quick, but 35 shouldn't make sense to you because that's an odd number. Remember, it's to the -1 charge, so it'll be 36. So 4 bonds times 2 is 8, and then we have 4 outer atoms. That's 4 times 6 is 24, and then subtract the 8 and the 24 from the 36, and that gives me 2 left over. All right, this should be a little bit more interesting. I don't think we've done one of these. So we have 6 sockets, 4 bonded, 2 non-bonded. The parent geometry is trigonal bipyramidal, and this is what it kind of looks like. And you could probably figure it out just by my drawing. So let's look at the note, little side note here, and that says there are 6 sockets on the central atom. The sockets contain 4 bonded pairs of electrons A and 2 non-bonded pair B. The parent geometry is square base bipyramidal. There are 4 square base atoms 90 degrees apart, A, and 2 polar atoms 180 degrees apart, B, in IF4 -1. The 2 non-bonded pairs are in polar positions, B. Therefore, it's going to be square planar. Square planar. Okay, let's put in our dipoles. And we'll see, even though it has kind of a bit of a strange geometry, it is indeed, you can see right from this drawing, that you will have bond symmetry and you will have no polarity. Okay, sulfur dioxide. Sulfur dioxide. I'll let this run a little bit, see if it makes sense. I'll keep quiet. Okay, there are 2 sockets on the central atom. Each double bond is treated as a single bond according to Vesper. There are no non-bonded electron pairs on the central atom. Therefore, it is linear. It is linear, and it will be non-polar. That should be self-evident that it should be non-polar. You see a lot of symmetry within the substance, and things are going to cancel, and it will be non-polar. Now, the next problem is very similar, except carbon has a valence of 4, where sulfur had a valence of 6, but things are going to be fairly similar. Fairly similar, and I'll just let this run through without any comments right till the end. And that's going to be nonpolar with bond symmetry. Very similar problem to sulfur dioxide. Now we're going to do chlorite. Chlorite, I-T-E. So we'll do the geometry first. Well, not the geometry, but as close as we can get it. And so now we'll see what we have. What adjustments do we have to make? We know we have 6, 6, and 7 plus 1. So that's going to be 20. And then 20 minus 4 is going to be 16. And then minus 12. So you'll should have 4 left over, which is 2 pairs. And let's see if we can do this jump ahead a little bit. So it's going to be like water, really. So it'll be bent with 2 excess pairs. The parent geometry will be tetrahedral. And I'll just let this play through. We should be getting fairly good at this by this time. Just like, same exact thing as to water. So we've seen this before, angular or bent, and it will most definitely have dipoles and no symmetry, and we will be yes to polarity. Three and 3.5. And now we're going to do chlorates. Chlorates. ClO3, -1 charge. This is problem number 10. We'll start off with a little bit of a trigonal geometry. So we're going to have 6, 6, 6, and then 7, and then 1, which is 26. And we're going to minus 6, that'll bring down to 20. And then we'll have minus another 18 because of the 3 atoms, 3 outer atoms, so it'll be 18. So it should be 1 pair left over. And that's going to go around the central atom, and that will make it, parent will be tetrahedral. And if I remove 1 bonded and put a non-bonded in its place, it's going to look like this. And let's read the note. This is, I don't think we've done one of these before. Fairly straightforward. There are 4 sockets on the central atom. The sockets contain 3 bonded pairs of electrons and 1 non-bonded pair. The geometry will be similar to ammonia. Ammonia is the classic one, NH3. Same exact geometry. And it'll be trigonal pyramidal. Trigonal pyramidal. And you will, of course, have dipoles towards the oxygen, but they will not cancel. There's not symmetry, and you will have polarity. And that concludes this practice session.